Hello again, this is Professor Roman. Let's continue our lectures on linear algebra. We come now to a famous algorithm known as the Gram-Schmidt algorithm for turning a sequence of vectors in an inner product space into an orthogonal sequence. So here we have a sequence B, V1, V2, and so on of vectors in an inner product space V. This could be a finite sequence or an infinite sequence. And the Gram-Schmidt algorithm will produce from this sequence another sequence O, U1, U2, and so on, that is orthogonal. Moreover, the span of B and the span of O will be the same. In fact, even the running spans are the same. The kth running span of B is the span, by definition, the span of the first k vectors, V1 through Vk. The kth running span of O is the span of the first k vectors in O. All the running spans for each k bigger than or equal to 1 are the same. So that is the connection between the two sequences. As I said, the original sequence, B, can be finite or infinite. It can be linearly independent or linearly dependent. We don't care. It can even contain zero vectors. I think you'll find that in many treatments of this subject at the undergraduate level anyway, the original sequence is assumed to be linearly independent, but that is not required. The consequences are only slightly different if the sequence is not independent, and we'll discuss that. Aside from the practical value, the Gram-Schmidt algorithm also shows that every non-trivial vector space of countable dimension actually has an orthonormal basis. And we will see that performing the Gram-Schmidt algorithm on a basis B for V, and then casting out any zero vectors that are produced by the algorithm, will actually produce an orthogonal basis for V, and that can then be normalized into an orthonormal basis. The Gram-Schmidt process is iterative, constructing a new orthogonal vector, U sub k, with each iteration. So here is how it works. For convenience, we'll let B sub k be the sequence consisting of the first k vectors in the original sequence. The first step in the algorithm is, I've got a little spelling problem here, is essentially to do nothing. We set U1 equal to V1 and O1 equal to the very short sequence containing only one term, U1. In other words, O1 is equal to B1. And so, of course, the first running spans are equal. After we have converted the first k vectors, B sub k, into an orthogonal sequence, O sub k, whose spans are the same, then to get the next orthogonal vector, this is what we do. Here is the space spanned by B sub k, which is the same as the space spanned by O sub k. We take the next vector, V sub k plus 1, the next original vector. I've drawn it so that it does not lie in this subspace, but it could be in the subspace. It doesn't matter. We project it onto the subspace that we've already formed, the kth running span. We take the residual vector. That vector is our u sub k plus 1. It's the next orthogonal vector. It is orthogonal to everything in this subspace. We've discussed this. And therefore, it is orthogonal to u1 through uk. So in simple terms, the Gram-Schmidt algorithm simply amounts to computing successive residual vectors. We have to check, of course, that the span of O sub k plus 1 is equal to the span of B sub k plus 1. But here's, by the way, the formula for the residual vector. So this is uk plus 1. It's vk plus 1 minus the projection onto the subspace O sub spanned by O sub k. And so we toss that in to O sub k to get O sub k plus 1. Note that the new orthogonal vector, uk plus 1, will be 0. This residual vector will be 0 if and only if vk plus 1 is in the span of bk, in other words, the span of v1 through vk. So if the vectors in B, the original vectors, are linearly independent, no zero vectors will be produced by the Gram-Schmidt algorithm. So we don't have to cast anything out in order to produce an orthonormal sequence. We just normalize the vectors. As to the new spans, the projection of vk plus 1 onto this subspace, of course, belongs to the subspace. So it belongs to the space spanned by OK, which is the same as the space spanned by B sub k. So I'm just going to set this ugly looking thing to W. Then the span of OK plus 1 is the span of the u1 through uk plus 1, which I can write this way. It's the span of O sub k plus the span of the single new vector u sub k plus 1. This is the same as this. The kth running spans are the same. And this u sub k plus 1 is vk plus 1 minus w. But the fact that w belongs to this subspace allows us to basically drop the w here and write this. And I'll let you think about that. And that is the span of B sub k plus 1. So the new running spans, the k plus first running spans, are also the same. And of course we just continue this process. If the original sequence is finite, the process will terminate. If not, it'll go on theoretically forever, but we will get an orthogonal sequence. And once again, if we want an orthonormal sequence, say n here, w1, w2, and so on, with the same span as the original sequence, we simply throw out any zero vectors that might have been produced by the algorithm, toss them out of O, and then normalize the remaining vectors. Throwing away zero vectors doesn't affect the span, of course. And then we normalize, and we'll get an orthonormal sequence with the same span as the original sequence. Now the orthonormal sequence might be shorter than the original sequence when B is finite, if we start with a finite sequence, the casting out of 0 vectors may reduce the size. If we're casting out any, we'll reduce the size of the sequence. And it can even turn an infinite original sequence into a finite one. And here's the most extreme example. If we start with an original sequence v, 2v, 3v, and so on, v non-zero, then the Gram-Schmidt process is going to, the first vector will be v, but then when we project 2v onto the subspace spanned by v, 2v is already in that subspace, the residual vector is 0. When we check, and 3v is in the subspace spanned by these two vectors, and so its residual vector will be 0, so all we're going to get is zeros after the first step. So the orthonormal sequence will just be a one-term sequence where we take v and normalize it. Okay. Here is the theorem that summarizes everything we've just discussed, so I won't go through it again. This theorem, the Gram-Schmidt process, does have an important corollary with respect to inner product spaces of countable dimension. As I mentioned before, V has an orthonormal basis. We're going to discuss the issue of which inner product spaces have orthonormal bases and which do not a little bit later. It's not not quite as simple as you might think. Anyway, an inner product space of countable dimension will have an orthonormal basis, and any finite orthonormal subset can be extended to an orthonormal basis for V. So for part 1, we've already discussed, if we take a countable basis, that's an independent set of course, perform the Gram-Schmidt process, we get an orthogonal sequence with the same span. Therefore that sequence will span all of V, and we can normalize to get an orthonormal basis. If we start with a finite orthonormal subset of V, call it O, then because the space spanned by O is finite dimensional, the projection theorem holds, and we can write this orthogonal decomposition. We know that the orthogonal complement of the space spanned by O has an orthonormal basis because it is also of countable dimension. So from part 1, we know there's an orthonormal basis, call it P, for this subspace. O, of course, is an orthonormal basis for the subspace that is spanned by O, and so the union is an orthonormal basis for V. There's a little bit of checking to do there. All the vectors in O are pairwise orthogonal. All the vectors in P are pairwise orthogonal. But what about a vector in O and a vector in P? Are they orthogonal or not? Well, I think you can see why they are. This corollary, by the way, part 2 in particular, does not hold in general for countably infinite orthonormal subsets. And here is an example. It's one we've seen before. It's this inner product space L2. This is an orthonormal subset. These are the sequences that have a single 1 in one position and zeros elsewhere. We've already seen that this sequence of vectors or sequences does not span L2. it spans the proper subspace of L2 consisting of the sequences with finite support. We've also seen that this has trivial orthogonal complement. So O is not contained in any orthonormal proper superset, because if it was, there would be a vector in the superset that was not in O. It would be orthogonal to all of these vectors. It would have to be 0, which is not part of an orthonormal set. So O is what we would refer to as a maximal orthonormal subset of L2. There are no strictly larger orthonormal subsets that contain O. So obviously then O can't be extended to an orthonormal basis. So part 2 of our earlier theorem does not hold when the subset is not finite. Example of the Gram-Schmidt process. Here are 3 vectors in R3. We'll write them in row format to save some space. We apply the Gram-Schmidt process. U1 is V1. U2 is the residual vector, V2 minus the projection of U1 onto the the projection of U2 onto the subspace spanned by U1. This looks a little more complex than what we've done earlier for projections, but that's because U1 is not a unit vector, so we have to divide by the norm squared to normalize both of these instances of U1. And it works out this way. Here is U3. It's V3 minus its residual, minus its projection onto the subspace spanned by U1 and U2, which is the same as the subspace spanned by V1 and V2. And it works out to be this. So we get these 3 vectors. They are orthogonal. They're non-zero because the original vectors were linearly independent, so no zeros were produced. Normalizing will give us an orthonormal basis for R3. Of course, there are many orthonormal bases for R3. The standard basis is. The point of this is that the space spanned by the original vector V1 is the same as the space spanned by W1. That's rather obvious since they're scalar multiples of each other. The space spanned by V1 and V2 together is the same as the space spanned by W1 and W2 together. The second running span are the same. That's not quite so obvious. If you compare V2 and W2, they don't look like they necessarily are part of the same subspace. Okay. And of course, then the third running spans are all of R3. So the point of this the point of this Gram-Schmidt process is to produce not just an orthogonal or orthonormal sequence, but one that is tied very intimately to the original sequence through the running spans, through the equality of the running spans. We mentioned earlier that the weighted integral inner products on the polynomial space, these are the real polynomials, are very important in applied mathematics, especially to the solutions of differential equations that arise in mathematical physics. So let's take a closer look at that. There are some very famous so-called orthogonal polynomial sequences. And I'm going to start the index with 0, because that's generally the way it's done. These are formed by picking a weight function that gives an inner product, weighted integral inner product, and apply the Gram-Schmidt process to the standard basis. So that's our original basis. Change the weight function, you change the inner product, you will change the resulting orthogonal sequence. In general, by the way, we don't normalize these sequences. The norm of the polynomials in these sequences is chosen by some other means, physical grounds or whatever. Don't just arbitrarily make them all norm 1. So let's look at 3 examples. If we start with the inner product, we take the weight function to be 1, then this is the inner product. And if we apply the Gram-Schmidt process to the standard basis using this inner product, we get a sequence of polynomials for which a sequence of orthogonal polynomials, p sub n of x. The polynomials that are then, we apply appropriate scalar multiples. We want this equation. So when n and m are different, the polynomials here are orthogonal. When m and n are equal, you'll get the norm squared of Pn of x, and that's going to be 2 over 2n plus 1. So the norm of each of these polynomials is the square root of 2 over 2n plus 1. So again, they're not normalized. They have some norm. By definition, their norm is chosen on some other grounds. These polynomials are called the Legendre polynomials. First introduced by Adrien Marie Legendre in 1782 as the coefficients in the expansion of the Newtonian potential. And I won't go into that. It's not appropriate for this course. They also appear, for example, in an expansion that looks like this, that has applications in physics. The polynomials h sub n of x defined this way are called the Hermite polynomials. So now our weight function is this exponential, e to the negative x squared over 2. And all these constants, the 1 over square root of 2 pi and the n factorial, again, are chosen on physical grounds. These Hermite polynomials were actually discovered by Laplace in 1810, before Hermite's contribution, so Laplace missed out on them being named after himself, got a bad deal there. These polynomials arise in a variety of applications: to probability, combinatorics, numerical analysis, and also physics. The polynomials defined by this orthogonality relation, here the weight function is just e to the negative x, are called the Legendre polynomials, introduced by Edmond Legendre in 1879. They are solutions to this differential equation and find applications in physics. For example, they're related to the Schrödinger equation for the hydrogen-like atom. And that's more than enough physics for this course. Just for practice, let's look more closely at the Legendre polynomials. So again, they're defined by this orthogonality condition. So this is the inner product. the weight function is equal to just the constant 1. So if we apply the Gram-Schmidt process to the original sequence of standard basis vectors, here are the computations. The standard basis vectors, by the way, are linearly independent, so we never have to worry about casting out any zeros. We can first normalize these polynomials. Those aren't the Legendre polynomials yet, but we normalize. So these are the norms of the polynomials we've collected so far. These are the normalized polynomials. So their inner product would be equal to just delta mn without this factor here. So this is what it looks like. Now we can make an adjustment to get this factor that we need for physical reasons or mathematical reasons, whatever it is. We just stick square root of 2 over 2n plus 1 in front of each of these. So these are the the Legendre polynomials. So that's how the first 4 Legendre polynomials would actually be computed. Well, we've seen that orthonormal bases are rather important, especially because their ability to express any vector in a very simple way, at least theoretically, as a linear combination of basis vectors. In other words, the coefficients in the linear combination are just inner products of the original vector with the basis vector. Finite orthonormal bases, which will be of concern to us as we proceed through this course, can be characterized in a variety of ways. And here is a theorem. Let O be a finite ordered orthonormal subset of an inner product space V. The following are equivalent. O is an orthonormal basis for V. Just to remind you, because the issue is going to come up in a little while, orthonormal basis means basis that is orthonormal. O is an orthonormal basis if and only if its orthogonal complement is trivial, or equivalently the subspace spanned by O has trivial orthogonal complement. This is equivalent to saying that every vector in V is actually equal to its Fourier expansion or to its projection onto the subspace spanned by O. This is equivalent to saying that Bessel's identity holds. We already know that Bessel's inequality always holds. The norm of V hat is a projection is always less than or equal to V, but O is an orthonormal basis if and only if the norm of V hat is the norm of V for all vectors. And finally, this is equivalent to Parseval's identity, which looks like this. It says the inner product of V and W, two vectors in the inner product space, is equal to the standard inner product of the coordinate coordinate matrices of the projections V hat and W hat with respect to O. What we know about the inner product from earlier discussions is that VW is equal to the standard inner product of the coordinates, because O is, well, actually I better be careful here. V and W have to belong to the space spanned by O. We're not assuming O is an orthonormal basis, we're just assuming it's an orthonormal subset. So for two vectors in the span, now O becomes an orthonormal basis for its own span. Then we know this because the Gram matrix of the inner product with respect to O is the identity matrix. So this is what we know, what we can say from earlier analyses. This is different because we have the projections on this side, the Fourier expansion, if you prefer. This is what the this inner product looks like. These are the coefficients. The first group here, these are the coefficients of the projection of V onto the subspace spanned by O, and same for the second components. All right, now, as to the proof, 1 and 2 are equivalent. This is a direct consequence of the projection theorem. We're dealing with a finite orthonormal subset, so it spans a finite dimensional subspace, this subspace, so we have this orthogonal decomposition, and so the subspace spanned by O is all of V, which is equivalent to saying it's an orthonormal basis for V, because we know it's independent if and only if the orthogonal complement is trivial. As for 2 and 3 being equivalent, first note that 3 here can be rephrased simply by saying that V minus V hat is 0. In other words, the residual vector for V is 0. So this says for all V, the residual vectors are 0. There's no residual vectors. Well, the family of residual vectors is precisely this orthogonal complement. And I will let you ponder that for a while. It's good practice. Okay. So this rephrasing of 3 is equivalent to the statement that this orthogonal complement is trivial. Okay. We know certainly that every residual vector belongs to this orthogonal complement. I shouldn't give it away, so I'll stop there. As to 3 and 4 being equivalent, this is a direct consequence of the Pythagorean Theorem. The residual vector, V minus V hat, is orthogonal to the projection. And so this, the Pythagorean Theorem gives us this. So V equals V hat if and only if the norm of V equals the norm of V hat. Finally, we need to tie in Parseval's identity. Well, if the first 4 equivalent statements hold, then the Gram matrix, so O is an orthonormal basis in particular, Gram matrix is the identity matrix, excuse me, and so as I mentioned earlier, the inner product of any two vectors V and W, now you see the span of O is everything. This is equal to the standard inner product of the O coordinate matrices and that is equal to the this standard inner product, because not only do we have all of 1 through 4 now, so v is equal to v hat. So I can just replace v by v hat, w by w hat. And that's Parseval's identity. As to the converse, we again do what I suggested here. We take this subspace spanned by O. It's an inner product space in its own right, using the inner product from V. And now O is an orthonormal basis for this space spanned by itself. And so the Gram matrix of the inner product on this space is the identity. And so the inner product of v hat and w hat, both of these belong to this subspace because they're the projections onto this subspace, is equal to the standard inner product of these two vectors, O-coordinate matrices. And Parseval's identity takes us from here to here. And so these two inner products are the same, which implies that the norm, if I said W equal to V, that the norm of V is equal to the norm of V hat. And that's number 4. And so 5 implies 4. And that's the proof. We discovered some time ago the change of basis formula for changing the coordinate system. If we want to change the coordinates from the B coordinate of a vector from the B coordinates to the C coordinates, we multiply by the change of basis matrix, which we've always denoted by M sub BC. What if we want to change orthonormal bases, go from one orthonormal basis to another? Well, let's take a look at how that might work. But so as not to interrupt this discussion we're about to have, we're going to discuss first a special type of invertible matrix. It will end up being the matrices MBC that do the change of orthonormal basis. So I want to take care of this now so I don't have to interrupt in the middle of our discussion. A square matrix A has orthonormal columns if and only if this equation holds. This is just think about how you take this product, and you will see you are actually forming the standard inner product of the columns, and it should be the identity matrix. Since A transpose and A bar now are invertible, we can, this is also equivalent to placing these two in the reverse order. A bar A transpose is the identity, and that is equivalent to the fact that the matrix A has orthonormal rows. Also, these equations are equivalent to this. A inverse is equal to A star. Okay. So this calls for a definition. A square matrix A is unitary if it has the following equivalent properties. It's invertible, and A inverse equals A star. Remember, A star is the adjoint of A, the conjugate transpose. The rows of A are orthonormal, the columns of A are orthonormal. These are all equivalent by some very basic matrix arithmetic. A real unitary matrix is often called a real orthogonal matrix, and I'll have something to say about that term in a second. Here's an example of a unitary matrix. The columns are orthogonal and unit vectors, and they're orthogonal. The rows are unit vectors and orthogonal. Now, I have to make a note of caution here about this unfortunate definition. The meaning of the term orthogonal, when we apply it to a matrix here, is not the same as the meaning when we apply it to vectors. A real orthogonal matrix, you might think, when you first hear that term, is a matrix with orthogonal columns. No, they have to be orthonormal by definition. I think it would have been better to call these real orthonormal matrices, but it's way too late for a change like that. So we're stuck with this term. A real orthogonal matrix has to have more than just orthogonal columns, it has to have orthonormal columns. Unitariness, the property of being unitary, is preserved by a variety of matrix operations, and I'm going to let you prove this for practice. The property of being unitary is preserved under product, inverse, transpose, and adjoint. You can do any of these things to unitary matrices and you still get a unitary matrix. Now, what about change of orthonormal basis matrices? What we have seen before some time ago is that the change of basis matrices, all of them, those are precisely the invertible matrices. And we've also seen that this equation, which I set up for you a long time ago, has the property that given any two of the three parts, an invertible matrix A, an ordered basis B, or an ordered basis C, given any two of these, the third item is uniquely determined. So there are two facts going on here. We characterize change of basis matrices. They are the invertible matrices. And we have this additional very useful property. We want the analog of these in the context of orthonormal bases. And for that, the first thing we need to decide is just what we mean by a change of orthonormal basis matrix. And here is the definition. I don't know whether you'll see this definition elsewhere or not, frankly. An invertible matrix A square, size n, is a change of orthonormal basis matrix if it has this form. It's a change of basis matrix for a pair of orthonormal bases. Okay. Any pair of orthonormal bases. So, which matrices are change of orthonormal basis matrices? Well, if A is such a matrix, we write out the definition of MBC, the column definition. So B and C are orthonormal bases. The old basis U1 through UN is here. We're taking the new coordinates. This is an old story we've seen many times. Well, because C is orthonormal, the Gram matrix is the identity matrix, and so the standard inner product of the C-coordinate matrices for ui and uj is the same as the inner product of ui and uj, but the B vectors are also orthonormal, and so that's delta ij. This just says that the columns of A are orthonormal. And so every change of orthonormal basis matrix is a unitary matrix. The converse holds. Suppose we have a unitary matrix. You can pick any orthonormal basis C for Fn and write this equation. A is given, C is given. C is an orthonormal basis. Therefore, we know that there is a unique basis B, u1 through un, that fits this equation. What we need to show is that B is orthonormal. That will tell us that A is a change of orthonormal basis matrix. Well, to see that B is no orthonormal, again, the Gram matrix with respect to C, because C is orthonormal, is the identity. So we have these same terms here, but in a different order. The inner product of ui and uj is equal to the standard inner product of their C-coordinate matrices. And now, because A is unitary, these columns of A are orthonormal, so we get delta ij, and so the u vectors are orthonormal. B is an orthonormal basis, A is a change of orthonormal basis matrix, so we are done. The change of orthonormal basis matrices are precisely the unitary matrices. And here's the picture. The big circle says the change of basis matrices are the invertible matrices. Inside the circle, the unitary matrices are the change of orthonormal basis matrices. It's a nice, beautiful picture. Also, if you go back, if you need to the discussion that gave us this result, you will see that because the inverse of a unitary matrix is unitary, the same argument will give us the analogous result, and that is, in this equation, A equals MBC, if we are given any two of the following, a unitary matrix, A, an ordered orthonormal basis B, or an ordered orthonormal basis C, the third item is uniquely determined. It's the same argument as before, or I should say an analogous argument. Now let's turn to the question of the existence of orthonormal bases in inner product spaces. We have seen that orthonormality is a strictly stronger condition than linear independence, in that every orthonormal set is linearly independent, but the converse, of course, is blatantly false. Linearly independent sets, there's no reason why they have to be orthogonal or normal or anything. So, question is, do all non-trivial inner product spaces have an orthonormal basis? The answer is no. How did we show that all vector spaces non-trivial vector spaces have an ordinary basis. We use Zorn's lemma. And Zorn's lemma, what we actually showed using Zorn's lemma, is that every non-trivial vector space has a maximal linearly independent subset, which we knew to be a basis. In an entirely analogous manner, Zorn's lemma can be used to show that every non-trivial inner product space, guess I better add that word, has a maximal orthonormal subset. So that's a subset that's orthonormal and that is not contained in any strictly larger orthonormal set. So this is maximal with respect to orthonormality, not with respect to linear independence. And those are not the same thing. Okay. Here's the theorem. I just stated it basically, but I've phrased it a little differently. Every orthonormal set in an inner product space is contained in a maximal orthonormal set. And so in particular, every non-trivial inner product space has a maximal orthonormal set. So let's suppose that O is an orthonormal set in V. We consider the collection of all orthonormal subsets of V that contain O. I'll make this subset. This is non-empty because it contains O itself. If we take a chain in this family, the union is in the family. It is orthonormal, and it contains O. It obviously contains O because each of the I sub k's that I have there, I think I have to change that to a k. Each of those contain O. What's left is to show that the union is orthonormal, and I'll let you ponder that. So every chain in the family has an upper bound. This is an upper bound, certainly, the union. And so Zorn's lemma tells us that A must have a maximal member. So once you've got a handle on Zorn's lemma, this is pretty straightforward. Now we need to be very careful. Since a maximal orthonormal set, M, let's say, is linearly independent, this might lead you to think that M is in fact an orthonormal basis, but it's not. Maximal linearly independent sets are not the same as maximal orthonormal sets. One of the consequences of the fact that orthonormality is strictly stronger than linear independence is that orthonormality can restrict the sizes of sets in such a way that no orthonormal set can be large enough to be a basis. Just as a hint, as sort of an indication to why this might be, if we take two vectors, V and W, that belong to the inner product space, and if they're orthonormal, so they belong to some orthonormal subset, let's say, then the Pythagorean Theorem tells us this, and so the distance between these two vectors is the square root of 2. In other words, they cannot be too close to each other. And so if the vectors in an orthonormal set are separated, that may cause cause there to be fewer of them than are required for a basis. This is all just sort of vague stuff, but it may help focus on what's going on. Okay. And we've already been discussing an inner product space where this happens, and that's little L2. And again, these sequences with a single one and all zeros. This is a maximal orthonormal subset, as we've seen. But it is not an orthonormal basis for L2 because it only spans the proper subspace of sequences with finite support. It's possible, that's not enough, but it is possible to prove, though I'm not going to do it here, that all maximal orthonormal subsets of L2 have the same cardinality, so they're all countable. And so none of these sets can span L2 because L2 is uncountable, and that's also something we won't prove. Uncountable dimension. So L2 does have maximal orthonormal sets, but it does not have an orthonormal basis. It does not have a maximal linearly independent set. So what we know is that every orthonormal basis is a maximal orthonormal set, because if you could enlarge it to a strictly bigger orthonormal set, if you could toss in at least one more vector and it was still orthonormal, that new set would be independent, linearly independent, and it would be larger than a basis. You know, strictly contain a basis. That's not possible. The converse doesn't hold. So here's a picture. Here are all the linearly independent sets in an inner product space. Here are the orthonormal sets. Here is a maximal orthonormal set, M. What does that mean? It means it's maximal in this universe among the orthonormal sets. The outer circle does not exist. If we enlarge the universe, we may lose maximality. Maximality is not an independent property. It's maximal with respect to some property. So maximal with respect to being orthonormal is not necessarily maximal with respect to being linearly independent. And we've seen an example where that's true. It's not, they're not the same. But despite the negative result here, if an inner product space should happen to have a finite maximal orthonormal set, so if M here is finite, then it's a different story. Then that will be a maximal linearly independent set. And that's a consequence of the Gram-Schmidt process. So let's say we have a finite maximal orthonormal set, script H, U1 through UN. So no bigger, you can't throw anything else in here and still be orthonormal. This is linearly independent because it's orthonormal. Is it a maximal linearly independent set? Well, if not, there's a vector, little v, for which we can toss it in, and this is linearly independent. Well, now we can apply one iteration of the Gram-Schmidt process. And what we can do is project V onto the span of these U1 through UN, take the residual vector, take the residual vector W, which is non-zero, because V is not in the span of U1 through UN. That's the whole point. P is linearly independent by assumption. We normalize, we end up with a larger, strictly larger orthonormal set. That contradicts the maximality of H as an orthonormal set. So H is also a maximal linearly independent set. Okay. So let's summarize. V is an inner product space. Any orthonormal basis, in other words, orthonormal maximal linearly independent set, is also a maximal orthonormal set. But the converse is not true. However, if V does have a finite maximal orthonormal set, and that would happen when V is finite dimensional, then the orthonormal bases are the same as the maximal orthonormal sets. In other words, maximality with respect to orthonormality is the same as maximality with respect to being linearly independent. Finally, maximal orthonormal sets, then, they may not be orthonormal bases, but they're still extremely important. They have a name, and it's a little bit unfortunate, but they're called Hilbert bases. It's the term basis that causes confusion. A Hilbert basis is not a vector space basis, necessarily. It's simply the term for maximal orthonormal set. Orthonormal sets that are maximal in their orthonormality. They're linearly independent, but they may not be maximal as with respect to linear independence. So to help avoid confusion, a vector space basis is often referred to then as a Hamel basis, to make the distinction with Hilbert basis. So this theorem we have tells us that orthonormal Hamel bases are also Hilbert bases, maximal orthonormal subsets. But the converse doesn't hold. However, if V has a finite Hilbert basis, then the two types of bases are equivalent.